Hello and welcome back to the sixth episode of Principles of Mathematical Analysis. This chapter is on the Riemann-Stieltjes integral. My name is Taha Arkian. I make the documents myself to avoid issues with the owners of the book. I'm just going to check if I'm recording. Great. Alright, let's start. So, you've seen the integral already in calculus. We just want to revisit the definition. So let AB be a closed interval on the real line. A partition P of AB is a finite ordered set of points A equals x naught less than or equal to x1 less than or equal to dot 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 less than or equal to xn minus 1 less than or equal to xn equals b. Each subinterval length is denoted by delta xi is equal to xi minus 1 for I is equal to 1 to n. This framework of partitions provides the foundation for defining the Riemann-Stieltjes integral. So basically you're taking points between A and B, no matter how many points, you're just taking points and you're basically dividing the segment or the interval A over B, A to B into multiple points, and you're taking the difference between those points to show the steps traveled at each point. And that's useful because we want to divide the graph of f into rectangles and describe the integral, and we'll see that later on. So let f be a bounded real function defined on AB for each partition P. Define m capital I is equal to supremum of f of x between this interval, and mi is equal to infimum of f of x between this interval. So between each between each division, you're taking the supremum of the function and the infimum of the function. So basically showing the highest limit points and the lower limit points. And with that, we can define the upper sum and the lower sum of f, like this. And this is basically the sum of all the rectangles below or above that graph of f, because if you take the upper sum, it's going to be that point is going to be greater than or equal to all the other points, so we can say it's above, quote unquote, it's above the graph of f. So we're approximating it from above with rectangles, and the lower sum is when we approximate it from below with rectangles. The upper Riemann integral and lower Riemann integral of f over AB are defined as the upper integral is equal to infimum of UPF, which is this one. So the infimum of the upper sums, and the lower integral to be the supremum of the lower sums. So basically you're saying I want the upper sum which is the lowest one. So you're taking the minimum upper sum, which means that it's the maximum point, right? It's going to be the lowest maximum point, and you're taking that to be the integral. Same thing here. You're taking the infimum. This time you're taking the supremum of it, so that you can find the minimum for it. Because the important part is to find if it's the lowest or the uppest one. So that's why we use infimum and supremum over all the partitions of P, right? And since we're talking about all partitions P, we can let the partitions become infinitely many, and find the infimum and the supremum, and that's basically the integral as you've seen it in calculus. And the integral exists when these two things are equivalent, and when it exists, we say that f is in R, which is the set of all Riemann integrable functions on AB. And we denote it by integral from a to b of f of x dx. Now, our remark is that basically b minus a, m times b minus a is less than or equal to LPF, is less than or equal to UPF, is less than or equal to m capital B minus a. And that's because the sum of all the delta x's that you're adding over here, as you see over here, is going to add up to b minus a. And we know that this m over here is going to be less than all these m's. So m times b minus a is going to be less than all this. And likewise, since this m is going to be greater than all these m's over here, greater than or equal to, you can say that all of this is less than or equal to m capital times b minus a, which means that the family of lower and upper sums is bounded. Now we have the following definition for, now we're talking about the Riemann-Stieltjes integral. So for partition P x naught to xn of AB, we define delta alpha I is equal to alpha xi minus alpha xi minus 1, where alpha is monotonically increasing function. Basically, that's the definition. So think of it like this. Instead of taking steps of between that interval, you're taking function of that step. So you're dividing the interval AB differently than the partition itself. So you're talking about different partitions now. You're taking the original partition, you're applying this function alpha to it, and you're taking the differences and you're setting those differences to be basically the steps of the integral that you want to integrate over. And yeah, that's kind of a way to look at it. For the practical or the visual view of this, you can think of it as basically the same thing as the original integral, right? Because you're taking steps in the x-axis, but now you're just taking it with function. So it's just another way, a quirky way, like a weird way of applying the integral, but it still works, right? And we want to show that this thing, when it works, the normal integral also works, right? So we define same definitions over here. So we define UPF alpha is equal to this, and LPF alpha is equal to this. And we define the lower Riemann-Stieltjes integral and the upper ones like this. And that's how you write the Riemann-Stieltjes integral. And when you take alpha of x is equal to x, the Riemann-Stieltjes integral reduces to the ordinary Riemann integral. That's basically what I was saying. And notice that the function alpha is not required to be continuous, as long as it is monotonically increasing, right? Because we don't really care if it's continuous. We just want the steps to increase each time, right? To be greater than 0. So the value of the integral a to b of f of d alpha depends on f alpha and the interval endpoints a b, but not on the particle symbol used for the integration variable. That's why we can just omit the x over here. We can just write it like this. We can write this like this. Okay, now we have refinements. We say that P star is a refinement of P if every point of P also belongs to P star. Equivalently, P is a subset of P star. So basically, when you have more points than the original partition and it contains all of those points, that's a refinement. Because it's like taking that and dividing it further. So that's where the name refinement comes from. Given two partitions P1 and P2, their common refinement is the union P star is equal to P1 union P2. That's the definition. Okay. Now we have the following theorem. If P star is a refinement of P, then U P star F alpha is less than or equal to U P F alpha, and L P F alpha is less than or equal to L P star F alpha. And this basically means that each time when you divide it more, the upper limit will decrease, the upper sum will decrease, and the lower sum will increase. And yeah, basically. Now the strategy for this is that we want to show that when we increase a number of divisions and keep the same thing, we can subdivide it further into two different parts and add them together. As you can see here, we subdivide it into two different parts, take that point, divide it into two different parts, and add them back together and subtract that unified part that was there before. So you're basically replacing locally that point where you've added an extra point. And like that, you can show that no matter how many points you add, this is going to be less than this, and this is going to be less than this. Okay, so let's read the proof. We just explained the strategy, so now let's read the proof. We first prove 9, okay? Suppose P star differs from P by a single additional point X star, inserted between two consecutive points xi minus 1 and xi of P. Let W1 equals infimum of f of x in this interval. That means the interval before X star and the interval after X star. So that's what we have. And Mi is the infimum of over all of this interval. Now, if we take the subtraction of this, of P star F alpha minus P F alpha, it's basically going to be all the common points of the partition will cancel out, right? We're just going to be left with this part, right? So we want to add this part and subtract this part because that's the remaining part, and the remaining part you're adding this because these are the new points and you're subtracting the old points. And this is going to be equal to this. You're just factorizing over here. So basically because mi times this plus mi times this, these things will cancel out, these x stars, and you're just left with this, right? So it's going to be the same thing as this term. So this factorization works. And now notice that this is greater than 0 because we know mi is less than w1 and it's also less than w2, as you said it here. This is greater than 0 because it's monotonically increased. This is also greater than 0, so all of this is greater than 0. Bring this to the other side and you have that LPF alpha is less than or equal to LP star F alpha. And we can repeat this k times. And you can do this the same thing for the upper sum. It's the same logic. Okay, let's move to the next theorem. For any bounded real function f on AB and any increasing function alpha, we have that the lower sum, the lower Riemann integral, sorry, the lower Riemann-Stieltjes integral is less than or equal to the upper Riemann-Stieltjes integral. Now, the strategy here is to use this inequality that we just obtained and relate it to these integrals, right? Because these integrals are basically when you take the supremum and infimum of all of this. So you want to apply this inequality to the infimum and the supremum to obtain the answer, which is going to be this. So that's the strategy. Now let's read the proof. Let P star be the common refinement of two partitions P1 and P2. By theorem 6.4, we have LP1 F alpha is less than LP star F alpha is less than UP star F alpha is less than UP2 F alpha. Because this is a refinement, this is a refinement. And we just use these inequalities over here. So that means LP1 F alpha is less than or equal to UP2 F alpha. Take the supremum over here and then take the infimum over here, and you're going to get this inequality over here. Now we have the following theorem. A bounded function f is Riemann-Stieltjes integrable with respect to alpha on AB if and only if for every epsilon greater than 0 there exists a partition such that UPF alpha minus LPF alpha is less than epsilon. And that makes sense because if we want the two lower and upper integrals to be equivalent, we need to have their difference less than some value that we can let go to 0 eventually for some partition. Right. So the strategy over here is to use it. It's two ways. There's two parts to this proof. One part is to use this inequality again, right? And when you use this inequality, you can replace these things with the lower and upper integrals and subtract them, and you know that this is going to be less than the other value over here. If we take this for granted, that's one part of the proof. The other part of the proof is to subtract the actual integral from the lower and upper integrals and make them less than epsilon over 2. So you're taking two parts. One part you're subtracting with the lower integral, and the other part you're subtracting with the upper integral. And like that, you can add them together, and you're taking two parts, dividing the epsilons by 2 so that you can add them together and get the result. So let's read the proof. Assume f is in R alpha with integral I is equal to a b f d alpha. So basically, just follow with me because it's not really well written over here. Basically, you take this inequality over here, and this thing, you take the supremum of it and the infimum of it, and you get the result. You basically get that this minus this is less than this minus this. So the upper integral minus the lower integral is less than or equal to u p2 f alpha minus l p1 f alpha, and we know this is less than epsilon, which means that the lower and upper integral when you subtract them is less than epsilon. So you can just let epsilon go to 0, add them together, and add together to get to the other side, and you're going to get that the lower integral is the same thing as the upper integral, which means that f is in R alpha. So forget this thing over here. So now for the second part of the proof, let I is equal to a to b f d alpha, given epsilon greater than 0, pick partitions p1 and p2, such that u p2 f alpha minus I is less than epsilon over 2, and I minus lp1 f alpha is less than epsilon over 2. When you add these together, let me just write it out. Let me write this out. You're going to get that u p f alpha is less than or equal to u p2 f alpha is less than integral of f d alpha plus epsilon over 2 is less than. Now notice, we know that integral of we know from this inequality over here, from this thing over here, you know that the integral is less than epsilon over 2 plus lp1 f alpha. So you know I is less than epsilon over 2 plus lp1 f alpha. So you take this over here, this epsilon over 2 plus this epsilon over 2 will give you epsilon, so you're going to get that lp1 f alpha plus epsilon. And we know, since it's a refinement, we know that it's less than or equal to lp f alpha plus epsilon. You let epsilon go to 0, right? So at the end you're going to get that this. Sorry, no, you don't let it. You don't let it go to 0. Plus epsilon. Subtract on both sides with LPF alpha, and you're going to get that UPF alpha minus LPF alpha is less than epsilon. That's what you're going to get, and that proves the result. Okay. Now we have the following theorem. If condition 13 holds for some partition P and some epsilon greater than 0, then it also holds with the same epsilon for every refinement of P. Okay. Alright. And suppose 13 holds for P is equal to x naught to xn, and let SITI be xi minus 1 to xi be arbitrary points, then the sum from 1 to n of fsi minus fti delta alpha I is less than epsilon, and the absolute value of the sum from 1 to n of fti delta alpha I minus the integral from a to b of f the alpha is less than epsilon. And to show this visually, let me just pull up the notebook again. Suppose you have a curve and you have a partition. When you take the SI and the TI, you're basically taking this thing over here, this point, let me put it in red, and this point over here. And let's say this is delta alpha, right? So at the end, you're just going to get a rectangle like this. And all these rectangles over here, when you add them together, this is logically, like if you think about it visually, is going to be less than all this over here. All this big rectangle stuff. So that's kind of the visual way to see the theorem over here. And this theorem over here, the third part of the theorem over here, it says that when you take any point over here, sorry, let me draw any point between the interval, and you take that corresponding y value, and you take rectangles from these, then this will eventually become the integral itself when you take finer and finer refinements, which makes sense because when you take finer and finer refinements, these things will approach with each other, and so you're getting the same range of values. So that's kind of like a visual way to look at it. Now if we want a strategy to prove it, let me just erase this. If we want a strategy to prove it, it's a different story. We can go to look at the proof. It's basically because when you take the upper sum, the strategy here is to compare it with subtracting the upper sum with the lower sum. Because when you subtract the upper sum with the lower sum, that thing, its range, the difference is going to be greater than when it's between the endpoints. Because when you subtract the upper sum from the lower sum, you're basically subtracting from the endpoints. But when you subtract from two different points between those endpoints, it's obviously going to be less. So that's how you prove the first statement. That's the strategy, and that also the proof. Now, we also got to put the statement, prove the statement for A, right? And how it works is that we use this inequality over here. This inequality over here. And since we know it works for some refinements, you can just subtract these two things over here, right? And add these together, and you're going to get that when it works for that thing, is going to work for all the refinements. That's the strategy. Basically, it comes from theorem 6.4. Let's go back. Yeah, it comes from theorem 6.4 as it says over here. And now for this, we know that LPF alpha is less than or equal to the sum from 1 to n of FTI delta alpha I is less than or equal to UPF alpha. And the reason why is that f of ti lies between m and m capital I, right? It's between those values. And you're having the same delta I. So we know it lies between these two things. And we know that LPF alpha is less than or equal to the integral of a to b of f d alpha is less than or equal to UPF alpha. And that's because this is the supremum of this, and this is the infimum of this, right? This is the infimum of this, right? So you have this inequality over here. So that means these two things lie between these two things. Subtract them together, and you're going to get that this is going to be less than or equal to the subtraction of these two things is going to be less than or equal to UPF alpha minus LPF alpha, right? And since it's less than that, and we know that that's less than epsilon, we know that we can also make this go less than epsilon, and that's the proof. That's the strategy. So you want to compare, the strategy is to compare it with the actual integral, and show that since with the sum corresponding to that actual interval is less than epsilon, and that's less than that thing, that's also going to be less than epsilon, which proves the statement. Now we have the following theorem. If f is continuous on AB, then f is an R alpha on AB. And here the strategy is to use the definition of continuity. And how we do that, basically, the strategy here is to use the definition of continuity and take the neighborhoods and the y value in the y-axis, multiply it by the neighborhood in the x-axis, and say that this is less than epsilon, to show that this thing is less than epsilon. Because okay, when you subtract these two things, okay, we want to show from continuity that this thing is less than epsilon. What's our strategy? Basically, our strategy is to use this definition that the subtraction of these two is the same thing as this. When you subtract the upper sum with the lower sum, you're still going to remain with the same steps in the x-axis. But you're subtracting from the y-axis, right? And when you're subtracting from the y-axis, you're going to be left with this neighborhood and the y-axis, which defines continuity. And you can use that theorem, you can use that property to relate it to epsilon. And since we know that we have this statement over here, we just let this be less than epsilon. So that's the strategy. And it's also the proof. Now we have the following theorem. If f is monotone on AB and alpha is continuous on AB, then f is an R alpha on AB. All right. So notice here we're not definitely saying that f is continuous on AB. You're just saying it's monotone on AB. And let's just read the proof and we'll explain the strategy later. Let epsilon greater than 0. Since alpha is continuous on AB, it is uniformly continuous by theorem 4.23. Then for any n in n, we can choose a partition P equals x0 to xn, such that delta alpha I is equal to alpha xi minus alpha xi minus 1 is equal to alpha b minus alpha a is divided by n. And we can do this because alpha is continuous. And since it's continuous, you can take the same steps with alpha, and you know that it's going to lie inside the function alpha. So you can do this. We're choosing this, okay. Assume f is monotonically increasing. The argument for decreasing function is similar. You're just using the inverse inequalities, right? Then for each I, mi is equal to f of xi minus y, f of xi minus 1. And m capital I is equal to f of xi, because we know it's monotonically increasing. So the least in the x-axis is going to be the least in the y-axis, and the most in the x-axis is going to be the most in the y-axis. Subtract these two together, you're going to get this sum over here. You're just going to replace it with this, right? And you're going to replace this with this. To get that as a sum from 1 to n of f of xi minus f of xi minus 1 of alpha b minus alpha a over n. And this thing over here, you can take this outside of the sum because it doesn't change throughout the sum. This thing over here, each time it's being like a diagonal. So we're going from 1 to 2, from 2 to 3, from 3 to 4. All these 2 to 2, 3 to 3, 4 to 4 to 4, all of these are going to cancel out, and you're just left with the endpoints, which is going to give you this thing over here, alpha b minus alpha a over n times f of b minus f of a. And as we let n large enough, this makes it less than, we can make it less than epsilon. So that's our strategy basically. The only strategy over here is to choose steps, equal steps, and since we're choosing equal steps, we can let it go to infinity, and we can make the difference between the sums go to 0, which means that it's going to be less than epsilon, and which means that f is going to be in R alpha. Now we have the following theorem. Suppose f is bounded on AB, has only finitely many points of discontinuity in AB, and alpha is continuous at each point where f is discontinuous. Then f is in R alpha. Okay, let's read the proof and I'll explain the strategy later. Give me a sec. All right. So the strategy over here is to take the points of discontinuity of f and remove them by removing the segments containing them. And by removing the segments containing them, we get a compact set. And we know since it's compact, it's going to be uniformly continuous on K. And then we use the definition of continuity on all the other points which are not discontinuous, right? Because we know that all those other points won't be discontinuous. Let's read the proof now. So after removing the small intervals uj, vj covering the discontinuities, the remaining set K in AB is compact. Then f is uniformly continuous on K. Hence there exists delta greater than 0 such that f of s minus f of t is less than epsilon whenever s, t, and k and s minus t is less than delta. Now construct a partition P is equal to x0 to xn of AB with the following properties. Each endpoint uj vj of the removed interval occurs in P. No interior point of any interval uj vj belongs to P. If xi minus 1 is not one of the uj, then delta xi is less than delta. Okay. So we're doing this because we want half of the intervals, kind of like around half of the intervals, if you think of it visually, to be less than delta. So we can use that property and show that it's going to be less than epsilon. Let's read the remaining of the proof. For such a partition, one checks that mi minus mi is less than or equal to epsilon, because we know that delta xi is less than delta. So we know that this thing, by definition of continuity, is going to be less than epsilon. That's why we're taking it to be less than delta, because we want some of the continuous points to satisfy this and then satisfy this, and we want the rest of the points to satisfy this thing over here. Mi capital minus mi is less than or equal to 2m capital. Because if you think about it, mi and mi over here, both one can be positive, the other can be negative, right? So it's like, if this is negative and this is positive, we know that this is less than this, and we know you're adding something to the m capital, right? But you know that it won't be the same thing as the m capital, so you know it's going to be lesser or equal to 2m. Arguing as in the proof of theorem 6.8, we then obtain UPF alpha minus LPF alpha is less than or equal to alpha b minus alpha a epsilon plus 2m epsilon. Because UPF alpha minus LPF alpha is a sum of mi minus mi capital minus mi times delta alpha, and we know it's 2m over here. This subtraction over here is 2m. Right. Okay. Yeah, an important point. This we chose the intervals covering the discontinuities. We chose them in a way such that when you subtract the endpoints, taking alpha is going to be less than epsilon. So, see, all of this construction comes together. If you want to explain the strategy at the end, we want to take we want to get rid of the discontinuities. We want when we're getting rid of the discontinuities, we're not getting rid of the endpoints. We want those endpoints to be multiplied by epsilon later. So that's why we choose it to be less than epsilon, so we can compare it to epsilon. And the other points, you can just take it to be less than epsilon by using the definition of continuity and choosing the distances to be less than delta. So you're fitting all of this together, right? And at the end, you're going to have both of these epsilons added together. And since epsilon is arbitrary, we can show that UPF alpha minus LPF alpha is less than or equal to epsilon. Okay, that completes the proof. Now, notice if alpha and f and alpha share a common point of this continuity, then f need not belong to R alpha. And there's actually exercise 3 for this. I mean, it's pretty obvious. If you think about an example where this might not work, is basically a function, a step function, where you're taking values between the steps, or taking one endpoint included and the other not included. And you're taking the alpha to also be discontinuous at that point, and you're going to see that the sums will give you different things, and it won't give you the integral, so it won't be in f won't be in R alpha. Now we have the following theorem. Suppose f is in R alpha on AB and m is less than or equal to f of x is less than or equal to m for all x in AB. If phi is continuous on m to m capital, and we define h of x is equal to phi f of x, then h is in R alpha on AB. Okay. So let's read the proof for this, and then I'll explain the strategy. Let epsilon greater than 0. Since phi is uniformly continuous on the compact interval m to m capital, there exists delta greater than 0 such that s minus t less than, not deltas, eta greater than 0 such that s minus t is less than eta implies phi of s minus phi of t is less than epsilon. Since f is in R alpha, there exists a partition P x from x naught to xn of AB such that UPF alpha minus LPF alpha is less than eta squared. Because we can let this go to any value, right? For any epsilon. So we can also let it go to eta squared, or less than eta squared. Let mi capital and mi denote the upper and lower bounds of f on xi minus 1 to xi, and let mi prime, m capital I prime, and mi prime be the analogous quantities for h. Divide the indices 1 to n into two sets. I in A if m capital I minus mi is less than eta, I in B otherwise. If I is in A, then by uniform continuity of phi, we have mi prime capital minus mi prime is less than epsilon, because you're just applying it to the function and you're getting the endpoints in the y-axis over here. Then mi capital minus mi is greater than or equal to, if I is in B, then mi capital minus mi is greater than or equal to eta. So by 18 we must have delta alpha I is less than eta. Why? Because let me write it out for you. We know that when I is in B, mi minus mi is greater than delta. So delta sum of delta alpha I is going to be less than or equal to the sum of mi minus mi delta alpha I is less than the delta squared. Because this is basically UPF alpha minus LPF alpha. It's analogous to that. And you divide the delta on both sides, you're going to get that the sum of delta alpha I is less than delta, basically. Actually, not delta. We're talking about eta over here. So let me change it over here. All of these are supposed to be etas. Yeah. So that's how we get this inequality over here. And notice the strategy was to square this so we can divide it later on and get this inequality over here. And again, we know that mi prime minus mi prime is less than or equal to 2k, where k is equal to the supremum of phi t. Again, like I explained earlier, is because you can't have it to be more than this, because the best case is that this is the worst case is that this is negative and you can't add this exactly the same thing. So it's going to be less than or equal to 2k. Okay. So that means UPH alpha minus LPH alpha is less than or equal to okay, let me write it out for you. UPH alpha minus LPH alpha, it's equal to the sum of mi star minus mi star delta alpha I for I in A, and then you also want the part where it's I in B. So you're adding them together. For I in B, mi star minus mi star. Delta alpha I. Okay. So when I is in B, this is we just said that this is less than or equal to 2k. This thing over here. And we know that this thing is one second. Yeah, we know that when it's in A, we just showed that mi star minus mi star is less than or equal to epsilon, because we know that mi minus mi is less than delta, which means by continuity that mi star minus mi star is less than or equal to epsilon. So this is going to be less than or equal to epsilon. So all this thing is less than or equal to epsilon and all the sum of the delta alpha I over here is going to be alpha b minus alpha a, which is the endpoints, plus, sorry, not delta. Each time I say delta, I mean eta. My bad. So, yeah, okay. Plus 2k eta over here. Why eta? Because we just said that the sum of delta A alpha, we just said that this is less than eta. So we're going to get this thing over here. And another really important part of the proof is that we choose eta less than epsilon. That's also very important, because here we want to show that this is going to be less than something times epsilon. So choose eta less than epsilon, and you're going to get epsilon alpha b minus alpha a plus 2k epsilon. And since epsilon was arbitrary, we proved the theorem. Now, the strategy here was, we have two functions. We're going from one to the other. We describe the endpoints of the first one and then the second one when it's applied. And basically, some of the endpoints, we let them less than delta, it's less than eta, and some greater than eta, so that we have two different parts, and one part implies this continuity statement over here. The other one doesn't. But what it does do, the other one, is that it implies that it's less than or equal to 2k, and we just add them together. So the strategy was to take, in more general terms, the strategy was to take the first step of the function and then apply the function back to it, take the endpoints mi and then mi star, and divide it into two parts related to epsilon, add them back together, and show that this thing over here is less than epsilon, or something times epsilon plus something times epsilon, which is going to be arbitrary. Now we have the following theorems. All right. Okay. So we know the sum of the integral is the same thing as the sum of the integral separated, and same thing when you multiply by a constant. And when f is less than or equal to g, then integral of f is less than or equal to integral of g. And we can divide the integral over two different endpoints, divide them, and then add them back together to get the same integral. The absolute value of the integral is less than or equal to m capital times alpha b minus alpha a. Okay. And when you take different alphas for the integrating step, you can just add them together, and same thing when you multiply by a constant. Now, the proof is very straightforward. We know that LP F1 alpha plus LP2 alpha is less than or equal to LP F1 plus F2 alpha. Because the infimum of x plus y is greater than the infimum of x plus the infimum of y, if you think about it. Because when you add values together, at that point where it has the infimum, the other one may not have an infimum. So when you add them together, it might not actually become an infimum in the next one. So that means that these two values added together won't necessarily be the same thing as this. And they're actually less than this. Why? Because you're taking the minimum of both things separately and not just the minimum of the actual thing. Let me give you a visual example. For example, you have let's say you have like f1 plus f2 is this, right? This is the infimum of f1 plus f2. Okay, but this thing over here this is f1, for example, and this is f2. Actually no, let's say this is f2. Let's say this is f2. Notice this thing plus this thing over here. This thing plus this thing is going to give you this thing. But notice the minimum of this is here and the minimum of this is here. But notice it's different from these 2 points. And you note this second point is greater than this first point. Is less than this first one, right? So it's always going to end up being something like this. Let me just close this. Okay. So we're going to get this. And same thing for the maximum now. The maximum is going to be the inverse process. And since now you can subtract this from this, and you know, since each of these is less than epsilon, this is going to be less than 2 epsilon, and since epsilon was arbitrary, we know that f is in R alpha. Okay. Now, if f is less than or equal to g, then all the upper bounds and the lower bounds are of the partition of the integral are going to be less than each other, right? So obviously the sum is going to be less than the other one, so that means the integral is less than the other one. And when you have different endpoints, you can separate the sum into 2 different sums from separating the endpoints, and those 2 different sums will give you 2 different endpoints, and the common endpoint that they share is C. So you're going to get the statement of the proof of the statement. And for D, when you want to show the absolute value of f is less than or equal to m alpha b minus alpha a. Basically, you know, negative m delta alpha I is less than or equal to mi delta alpha I is less than or equal to mi delta alpha I is less than or equal to m delta alpha I. Right? So if you take the absolute value, all of this is going to be less than m delta alpha I added together and together and together. And this chain is going to give you alpha b minus alpha a. So at the end, it's just going to give you that it's less than or equal to m times alpha b minus alpha a. And this works because it has linearity, basically. When you're adding 2 steps together, when you can just expand the product and it just becomes an addition, right? And same thing for when you multiply it with C over here. And you can say that UPFC alpha is equal to C UPF alpha, and LPFC alpha is equal to C LPF alpha. Now, all right. Okay, we proved that this thing over here is in R alpha, but we didn't show that the sum is precisely this. Now that's what we're doing over here. That's the part we skipped. I added it later on over here. So with the same P, we also have UPFJ alpha is less than integral from a to b of fgd alpha plus epsilon. That's because we showed that their difference is less than epsilon in the theorem over here. If we go back, it's a low, yeah, this thing over here. So that you're going to get this result over here. Yeah. So integral of f plus f1 plus f2 d alpha is going to be less than or equal to u pf1 plus f2 alpha, because it's always going to be like a refinement of this when you're approaching the steps. You're taking the partition, you're taking infinitely many points, right? This thing is going to be less than the integral from a to b of f1 d alpha plus integral of a to b of f2 d alpha plus 2 epsilon. So you're just taking this inequality over here and adding them together to get that is this. And since epsilon was arbitrary, we get this inequality over here. And if we replace the f1s and f2s with negative f1 and negative f2, you're basically multiplying by negative 1, right? So it will flip the inequality, and we know it works. You can take any function to be the negative of another function, and since we know the negative of a function works with this inequality, that means that the inequality works on both sides like this. So on this side and on this side, and that means the integral of a to b of f1 plus f2 d alpha is equal to integral of a to b of f1 d alpha plus integral of a to b of f2 d alpha. Now we have the following theorem. If f and g are in R alpha on AB, then fg is in R alpha, and integral of a to b of f d alpha, its absolute value is less than or equal to the integral of a to b of the absolute value of f d alpha. This works because 4fg is equal to f plus g squared minus f minus g squared, and notice f plus g, f minus g are their sums and subtractions of a function, so they're also going to be in RA. We know that x squared is a continuous function, so the square of this is going to be in RA, the square of this is going to be in RA, so their subtraction is also going to be in RA. So this thing is in RA, divided by 4, and you're going to get that fg is also in RA, or R alpha. Now, we apply the theorem of continuity with phi t is equal to absolute value of t. So the absolute value of f is in R alpha. We can choose c is equal to plus or minus 1, so that c integral of a to b of f d alpha is equal to the absolute value of f d alpha, because the absolute value is basically taking either plus 1 times that value or negative 1 times that value, which is what we're doing over here. Okay, so now we know that this is equal to CF the alpha, we took this C inside the integral now because it has no difference. And we know that CF is less than or equal to the absolute value of F, because we don't know always for sure if that when we're flipping that F or keeping the... Okay, we don't always know if negative F or F is going to be less than or equal to no. Because when you have F, okay. It's either going to be the same thing as the absolute value of F when you have CF, or it's going to be less than that. Why? Because suppose F is positive, this is positive. Okay, let's make a visual example, I guess. Okay, so let's say this is F. This is the absolute value of F, this thing over here. This is the absolute value of F. That's F. And this is this thing over here in purple. I'm going to draw it as negative F. See, this red thing, red is greater than pink. And the reason why is that let's say it in more rigorous terms. I want to show this in more rigorous terms. So CF, we don't know if it's greater or less than F. Okay. Let's just write it like this, right? Okay. CF, F. If F is greater than 0, we have C is like this, which is equal to plus or minus 1. And we know in this case it's going to be less or equal to, because we know that C is plus or minus 1. So it's going to be less or equal to this. Plus or minus, because plus or minus 1 is less or equal to plus or minus 1. Now if F is less than 0, the sign will be flipped. So it's going to be like this. Sorry, this is going to be plus, this is going to be positive 1 over here, right? It's going to be equal to positive 1. And we know that C is equal to negative 1 or 1, so that's less or equal to positive 1. And now here, this is equal to negative 1. And we know that C is greater than or equal to negative 1, because it's either 1 or negative 1. But since we flipped the inequality, because we multiply by negative, we just backtrack to it and we show that CF is less than or equal to the absolute value of F. In both cases, this works. And we're going to get this thing over here. Okay. Give me a second. All right. Now we have the unit step function I is defined by I of x is equal to 0 when x is less or equal to 0, and 1 when x is greater than 0. So basically a jump between 0 and 1 at x is equal to 0. Now we have the following theorem. Let A less than S less than B. Suppose f is bounded on AB and continuous at S, and define alpha x is equal to I of x minus S. Then the integral of f of d alpha is equal to f of s. And that makes sense. Why? Because the only point where it's going to become 1 from that point afterwards is going to be s. And you're just going to be left with f of s, and all the other points will cancel out. So at the end, you're just you're adding all the rectangles, and you're just going to be left with f of s that's remaining because all the other rectangles will cancel out. So that's the results you're getting over here. That's kind of like the strategy and the visual way to look at it. Let's read the proof. Consider partitions of the form P is equal to x0, x1, x2 to x3 with x0 is equal to A, x1 is equal to S. S is less than x2, less than x3 is equal to B. Okay. So LPF alpha is equal to M2, and LPF alpha is equal to UPF alpha is equal to M2, where M2 and M2 are the infimum of supremum of f on S to x2. X2 was okay. Yeah, because all the other points before S are going to go to 0. So we just want to look at the interval between S and x2. That's the remaining integral. So we're taking the lower sums and the upper sums in that interval. And since x2 goes to S, both m2 and m capital 2 converge to f of s by continuity. Thus the integral equals f of s. That's basically what we're saying. So now suppose Cn is a sequence of non-negative real numbers with n is equal to 1 to infinity of Cn is less than infinity. And the sequence Sn is a sequence of distinct points in AB. Define alpha of x is equal to the sum of n equals 1 to infinity of Cn I x minus Sn. If f is continuous on AB, then the integral of AB from A to B of f d alpha is equal to the sum from 1 to infinity of Cn f of S7. So that's really interesting because now we're transforming the integral into a sum, into an infinite sum. And a way you can think about this is that we just proved that this thing, when you take the step function to be this, is equal to f of s. So now if we take the step function to be c of n times this thing, it's going to be c of n times f of s of n. And since it's going to be this step function is actually a sum, we know that the sum of the step function is the sum of the integral of the integrals. So you're going to get the sum of all of this, so it's going to be the sum of n equals 1 to infinity of c of n f of s of n. So let's read the proof and I'll explain the strategy. The series in 22 converges pointwise for every x since the sum of c of n is less than infinity. Because this is less than or equal to the sum of c of n, right? Its sum alpha x is monotonically increasing with alpha f a is equal to 0 and alpha of b is equal to the sum of c of n. Because alpha of b is when you get through all the points, and you're going to get to the sum of c of n. Okay, wait. Yeah, exactly. Fix epsilon greater than 0. Choose n capital so large that the sum from n plus 1 to infinity of c of n is less than epsilon. Split alpha into two parts. Alpha 1 of x is equal to the sum from n equals 1 to n capital of c n I x minus s n. And alpha 2 of x is equal to the sum of n plus 1 capital to infinity of c of n I x minus s of n. This thing over here, when you take the integral, is going to give you this thing over here, because it's just the same thing as this. You're splitting the integrals between the sum of these things, and each time you're multiplying by c of n. So each term is going to be c of n times f of s of n, and you're adding them together. Let m capital be the supremum of f of x from x is equal to x in AB. So exactly, that's the strategy. The strategy is just to use this again and describe it as a sum of these things together to get to the result. We know that the absolute value of this is less than or equal to m capital times alpha 2b minus alpha 2a, which was a theorem we just showed previously. And alpha 2b minus alpha 2a is actually the sum from n plus 1 to infinity of c of n. Because we know that this alpha 2 of a, give me a second. I'm not sure about this. Forget this part over here, okay? Forget this part. We know that alpha 2b minus alpha 2a is less than epsilon. Actually, wait. No, this is correct. This is correct. So basically, alpha 2b minus alpha 2a is equal to this thing over here. And the logic behind that is that the logic behind that is alpha 2 of x is equal to this over here, right? Okay. Give me a second, okay? I'll be back. Okay, so I'm back. All right. This thing over here is less than this thing over here. So evaluating this at B is going to be less than this, and evaluating this at A is going to be less than this. So subtracting this is even going to be less than that. So it's going to be less than this, and this is less than epsilon. So this is going to be less than m capital epsilon. Thus, okay. We know that alpha is equal to alpha 1 plus alpha 2. So this integral is going to be this. uh, and we know that f of the alpha 1 is equal to this over here, right? So it's going to f of the alpha 2, this thing over here, is going to be the same thing as the integral of ab of f d alpha minus this thing over here, not the alpha 1. So it's going to be this minus this thing over here inside this parentheses, because it's the full integral is the sum of the two separate integrals. So if you want to find the sum of the second, if you want to find the integral of the second alpha, you take the full integral minus the integral of the first alpha. So it's going to be the integral of the first, the full integral minus the integral of the first alpha, which is this sum over here. So it's going to be the same thing as the integral of the full integral minus the sum of Cn f of Sn, and we know that's less than m epsilon. And as n goes to infinity, we can obtain that it's less than epsilon, and which means that the full integral is the same thing as this sum over here, which proves the statement. Yeah, exactly, this thing over here. If you read it, it's the absolute value of a to b of f d alpha minus the sum f n is equal to 1 to n capital of Cn f of Sn is equal to this thing over here, which is this thing is less than m epsilon. So we get this thing over here. Now, we have the following theorem. Assume alpha is monotonically increasing on AB, and that alpha prime exists and it's Riemann integrable. Let f be a bounded function on AB, then f is in R alpha, means f of A prime is in R, and in that case f of the integral of f of the alpha is equal to integral of f of x alpha prime of x dx. So it makes sense, because when you're taking the d of an alpha, it's analogous to the derivative, as you've seen in calculus, so it's going to give you this thing over here. But we want to prove it, and we need a strategy, and I'll explain that later. Let epsilon greater than 0, since alpha prime is in R. Theorem 6.6 guarantees a partition P is equal to x naught to xn of AB such that UP A alpha minus LP A alpha is less than epsilon. Because it's Riemann integrable, so this inequality that we just proved works. By the mean value theorem, for each I there exists Ti in xi minus 1 to xi, with delta alpha I is equal to alpha xi minus alpha x minus 1 is equal to alpha prime of Ti delta xi. Exactly, that's the strategy over here. The strategy is to use a mean value theorem and relate it to the derivative of alpha times delta x. And since we know that when we're taking these values between xi minus 1 and xi, and we know that their integral is the same thing as we're basically using this property over here. Let me show you. We're using the fact that the sum of I to n of fti delta alpha I minus the integral of ab of f d alpha is less than epsilon, which is the statement we proved earlier. We're using that here. Let's just go back. Okay. Now let Si be in xi minus 1 to xi be arbitrary by theorem 6.7b and the inequality, which is basically, again, let's just go back again, is this property over here that the sum of f of Si minus f of Ti times delta alpha I is less than epsilon, which is the thing we proved earlier. So we're using these two properties over here. Okay. This is going to be less than epsilon. Let m capital be the supremum of f of x, the absolute value of f of x. Multiplying by m gives us the sum of I to n of f of si alpha prime of si delta xi minus the sum of I to n of f of si times alpha prime of ti delta xi, because all the f of si's over here, their absolute values are going to be less than the absolute value of this over here. So all of this is going to be less than this m over here times this epsilon, because we multiplied by f of x on both sides. All right. Okay. Yeah, we're just replacing this thing over here with this thing over here. Because that's the definition of delta alpha I. Okay. So we're going to get this inequality over here. And UPF alpha is going to be less than or equal to UPF alpha prime plus m epsilon. And UPF alpha prime is going to be less than or equal to UPF alpha plus m epsilon. Because this thing over here, if we take the absolute value separately and add it on both sides, we're going to get that this thing, and take the supremum, this is going to give you this, and this is going to give you this, added on with m epsilon is going to give you this. And same thing over here, because now you can, when you have the absolute value, is the same thing of the negative, the absolute value of that negative thing. So basically, for example, the absolute value of 1 is the same thing as the absolute value of negative 1. And you use the same idea, separate the absolute value between the subtraction. So and that's going to be less than this thing over here, which is less than this thing. So it's also going to be less than m epsilon. Added on the other side, you're going to get that UPF alpha prime is less than or equal to UPF alpha plus m epsilon. Use these two facts, gives that the absolute value of this is less than or equal to m epsilon. And instead of taking the supremum, if you take the infimum, it's going to give you this thing, and it gives you, it proves the theorem that the integral is actually the same thing as f of x times alpha prime of x dx. Okay. Now, the interesting thing is that now we can talk about the moments of inertia too, because the moment of inertia is actually the integral of x squared times the mass, times the derivative of the mass. It's basically the resistance of a material if you think about it physically. And if you want to look at it with two integrals or three integrals, is going to be the double integral of x squared dy dx, or the double integral of y squared dy dx, depending on if you want the moment of inertia of the x-axis or the y-axis. and it's going to be the triple integral of x squared plus y squared, x squared plus z squared, etc. like that, if you want it for 3 dimensions. Okay. So the interesting thing is that now we can talk about these things. We can replace the variable of the differential variable with something else, and we can also express the integral as an infinite sum, which is really interesting. Now we have the following theorem, which is a change of variables. So it's basically saying that you can change variables and the bounds of the integral. And the strategy here is to basically, because you're doing composition of functions, you can choose a partition such that when you choose that partition, it's going to okay, so you're using a partition such that when you choose the x values and the y values, it gives you the same thing. So that when you take the function as at those x values, is going to give you the same as those y values. So you can get the same values for these partitions, and basically you're going to get the same lower and upper sums. Let's read the proof now. For each partition P is equal to x0 to xn of AB, let Q is equal to y0 to yn be the corresponding partition of AB with xi is equal to phi yi. Every partition of AB arises in this way. Since f takes the same values on xi minus 1 to xi that g takes on y minus 1 to yi, we're going to have LQG beta is equal to beta is equal to LPF alpha, and UQG beta is equal to UPF alpha. And because f is an R alpha, partition P can be chosen so that both upper and lower limits are arbitrarily close to integral of AB f d alpha. And we're going to get the result. All right. All right, I'm back right now. Let's continue. Theorem 6.2, integration and differentiation. Right now we want to get to the fundamental theorem of calculus. That's our point. So let f be an R on AB. For a less than or equal to x less than or equal to b, define f capital of x equals to the integral from a to x of f of t dt. Then f capital is continuous on a to b. If f is continuous at a point x0 in AB, then f is differentiable at x0, and f capital prime of x0 is equal to f of x0. So we're showing that the integral is actually the antiderivative. Let's read the proof now. So the proof, the strategy, as you can see here, is kind of using the fact that this thing over here is equal to this thing over here, and relate this to the derivative somehow, you know. So let's read the proof and I'll explain the strategy more precisely later. Since f is an R, it is bounded. Say absolute value of f of t is less than or equal to m capital for a less than or equal to t less than or equal to b. If a is less than or equal to x less than y less than or equal to b, then by theorem 6.12, the absolute value of f of y minus f of x is equal to the integral from x to y of f of t dt. This is because both of these have starting points at a. This f of y and f of x, they have starting points at a. This finishes at y and this finishes at x. So the common part starting from a will cancel out, and you're just left from the endpoints being x to y. That's why you have the integral from x to y over here. And this thing over here is less than or equal to m capital because f of t is always less than or equal to m, and the dt's accumulated together will give you y minus x. So it's less than or equal to m capital times y minus x. This shows that f capital is uniformly continuous, hence continuous on AB. Give me a second. Let me just look at the book. Yeah, here there's something missing over here. This is provided that y minus x, the absolute value of y minus x, is less than epsilon over m, right? So this thing becomes epsilon over m multiplied by m. It will give you that this is less than epsilon. So for any epsilon, you can choose a delta so it works. So that means it's continuous on AB. Now assume f is continuous at x0 in AB. Given epsilon greater than 0, choose delta greater than 0 such that f of t minus f of x0 less than epsilon whenever t minus x0 is less than delta. For 0 less than h less than delta, one second. We have f capital of x0 plus h minus f capital of x0 over h is equal to this thing over here, which makes sense. As I said, we're switching the endpoints because we're subtracting integrals, and we know they have common parts, these two integrals. So we're just left with this integral from x0 to x0 plus h, and we divide the whole thing by h, and we get this result. Subtracting f of x0 gives this integral over here. And the reason why is that this thing, when you integrate it, it will give you f of x0 times t. Now, okay, we haven't shown the fundamental theorem of calculus yet, so let's not talk about it like that. And a way you can see this is forget, okay, by theorem 6.12, let's look back at theorem 6.12. Theorem 6.12, okay. Okay, so yeah, just you don't because you could say that you need to use a fundamental theorem of calculus here to say that this is f of x naught times t and then apply it with on these endpoints. But something that we saw earlier on is that we don't really need a fundamental theorem of calculus here, because we know that when something is constant, the sum of the constant, you can take it out of the integral, and you'll just be left with the overall step, which is the difference of the endpoints. So at the end, it's going to be f of x naught times x naught plus h minus x naught, which is f of x naught times h. Divided by h, it will give you again that it's f of x naught. So these two sides are equivalent. And now you can take the absolute value on both sides. we know that this thing over here is f of t minus f of x naught, right? So it's going to be less than epsilon. And when you divide it by h, it's it depends if h is between 0 and 1. So let me just think about this. Yeah, exactly. This thing over here is going to be less than epsilon. So replace this with epsilon over here. And now this whole integral over here will be epsilon times x naught plus h minus x naught. So it's going to be epsilon times h, divide that by h, it's going to be epsilon. So this thing over here is less than epsilon. So this thing is less than epsilon. Take the absolute values on both sides. That means this thing, which is actually the derivative when you let h go to 0, and this thing are equivalent. So that means this thing is actually the derivative of this thing, and we prove that f prime capital of x naught is equal to f of x naught, which proves the theorem. Now we have the fundamental theorem of calculus, which is basically when you take the antiderivative on both endpoints and you subtract them. So like this. For the proof of this, let's read it and I'll explain the strategy later. Let epsilon be greater than 0. Choose a partition p equals x naught to xn of ab such that UPF minus LPF is less than epsilon. Because you know f is in R, right? That's our assumption. By the mean value theorem, for each I, there's ti in xi minus 1 to xi, with f of f capital xi minus f capital of xi minus 1 equals f of ti delta xi. So the strategy here is to use the mean value theorem and relate the sum of this of the differences to be actually the sum of the derivatives, as you see here. So f of xi minus f of xi minus 1 is equal to f of ti delta xi. Summing over i's give us that f of f capital of b minus f capital of a is equal to the sum of f of ti delta xi. By theorem 6.17, any such tagged sum differs from sum of abf by at most UPF minus LPF is less than epsilon. Hence, this thing over here is less than epsilon. Because you can let the partitions become smaller and smaller, or choose partition which gives you that this is actually the integral. So if this is the integral, then yeah, exactly. This is f of b minus f of a over here is this sum over here. Okay, now this sum over here, when you take the supremum, is going to be this thing over here. So you can just replace this with this. So you can replace this f of b minus f of a with u of pf. And LPF, you know, when f is in R, LPF is just the integral. So you're going to get f of b minus f of a minus the integral of a to b of f of x dx is less than epsilon, which shows that the integral is actually equivalent to f capital of b minus f capital of a. And now we have the theorem of integration by parts, which gives you this formula. So basically the integral from a to b of f of x gx dx is equal to f capital of b g capital of b minus f capital of a g capital of a minus the integral of a to b f of x g capital of x dx. And this is famous in calculus when we say integral of u dv is equal to uv minus the integral of v du. This is a famous formula. And the technique here, take this on the other side, right? So f capital of x times g of x plus f of x times g capital of x. This is actually what? This is the derivative of f capital of x times g capital of x. So we know the integral is actually the antiderivative. So that means that the integral is actually f of x times g of x. Okay, f capital of x times g capital of x, and we apply it on both endpoints, and we're gonna get this. And you can just bring that back to the other side, and we're gonna get the formula over here. Which is basically what is explained over here. So the strategy is to relate it with the product of the two functions and then integrate it. And we can have integrals for vector valued functions, which is basically just integrating over each component. And it's identical when we say the fundamental theorem of calculus for vector valued functions, because you just apply the argument to each coordinate of f of x. And we have the following theorem. Let f go from AB to Rk and assume f is an R alpha for some monotonically increasing alpha on AB. Then the absolute value of f is an R alpha, and the absolute value of the integral from a to b of f of the a is less or equal to the integral from a to b of the absolute value of f the alpha. So the strategy here is to say that the absolute value is actually equivalent to this statement over here. So it's equivalent to the square root of the square of the functions added together. And we know that the squares are in R alpha. And we know since the squares give always a positive result, root of x takes only positive results. And therefore, if it only takes positive results, we can say that it's 1-to-1. And so the mapping x to root of x is continuous on every interval 0 to m. So that means the absolute value of f is also in R alpha. Now, when we want to prove that this is less than or equal to this thing, all we do is we say that y is equal to the integral of f without the absolute values. Now we take the dot product of y with itself, which gives you the norm of y squared. So it's going to be the sum of the components, which are the integrals, squared. And this is equivalent to the sum of the yj, which are the components, times the integrals of fj, which is also the same thing as yj. So we're describing the components in two different ways and using that as a strategy. And now we can take the sum inside the integral because it doesn't change anything. And we're going to get that it's going to be the integral from a to b of the sum of yj f of j x d alpha x. And we know that this is actually the dot product between these two things, and we know that's less than or equal to multiplying the norms of the things themselves. So the other strategy here is to use the Cauchy-Schwarz inequality. So this is going to be less than or equal to absolute value of y times the absolute value of f of x. And so we're going to get that the absolute value of y squared is less than or equal to the absolute value of y times the integral of a to b f of absolute value of f of x d alpha x. Divide the absolute value of y on both sides, and you're going to get the inequality, which is this. Now we have rectifiable curves. Basically, you can have mappings from a segment AB into RK. And we call this a curve. And if it is 1-to-1, we call it an arc. And if the endpoints are equivalent, we say that the curve is closed, which is pretty self-explanatory. And we define the polygonal length of the curve, and basically the logic here is to take gamma of xi minus the gamma of xi minus 1, which is basically the vector going from one point of the curve to another point. So it's like a segment on that curve, kind of like, right? And if you take the absolute value of it, you're going to get the length of that. And when you add the individual lengths, you're going to kind of approximate the length of the curve. And if you want the actual length of the curve, we define it as the supremum over all the partitions of uh, uh, AP gamma. It's not really an A, but it's an inverse V. I don't really know how to call it. And we say it's rectifiable when the length is less than infinity. Because notice you can have spirals that don't end in a finite range. So you don't really like those kind of curves. We want to deal with simple curves that actually have a length. That's why we call it rectifiable. And notice when we're in notice that the length is actually the same thing as the integral from a to b of the norm of the derivative of a gamma t dt, and we're going to prove that. And let's prove it, and I'll tell you the strategy later. So okay, if a is less than or equal to xi minus 1 is less than xi is less than or equal to b, then gamma of xi minus gamma of xi minus 1 is equal to the integral of xi minus 1 to xi of gamma prime of t dt, because that's from the fundamental theorem of calculus. And we just proved the property that the absolute value is less than or equal to the integral of the absolute value. So we use this property over here. Hence, for every partition P of AB, V inverse, how should I call this? Let's just call it A. AP gamma is less than or equal to the integral from A to B of gamma prime t, its absolute value of dt. So we proved one part of the inequality. Now we want to prove the other side of the inequality to say that these two statements are actually equivalent. And to do this, notice continuity is very important here. And if we don't use the property of continuity, we can't really get to this conclusion. Why? Because if it's not continuous, you can't really define the differences of the vectors on the curve, and you can't really relate it to the derivative. So it's really useful to use the notion of continuity over here. So we know that we know that the y prime is continuous. Sorry, gamma prime is continuous on AB. So we know that by continuity, the absolute of gamma prime s minus gamma prime t is less than epsilon whenever s minus c is less than delta. And let P equals x0 to xn be a partition of AB with delta xi less than delta for all I. If xi minus 1 is less than or equal to t is less than or equal to xi, it follows that the absolute value of gamma prime t is less than or equal to absolute value of gamma prime of xi plus epsilon. Notice the reason why we chose delta xi is less than delta over here. Oh, sorry, my bad. The reason why we chose this is because this thing over here, you can take this to the other side and say the absolute value of gamma prime of t minus the absolute value of gamma prime of xi, which is analogous to the absolute value of gamma prime of s minus gamma prime of t. And we know this works. Gamma prime of s minus gamma prime of t is less than epsilon whenever s minus c is less than delta. So if we take delta xi is less than delta, that means that it will lie in that neighborhood, so it will also satisfy that thing. So we can basically say that it works for t and xi too. And we know that the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. So we can use that property and take it to the other side to say that the absolute value of gamma prime of t is less than or equal to the absolute value of gamma prime of xi plus epsilon, following from this statement over here. Hence, the integral from xi minus 1 to xi of gamma prime of t dt is less than or equal to the absolute value of gamma prime of xi times delta xi, because basically all of these values are less than gamma prime of xi, and from xi to xi minus 1 is delta xi, and same thing for here, so you multiply delta xi times epsilon. Now we know that the absolute value of gamma prime of xi times delta xi is equal to the integral from xi minus 1 to xi of gamma prime of t plus gamma prime of xi minus gamma prime of t dt. So we added this gamma prime of t and subtracted this gamma prime of t. And now we separated with the triangle inequality. Therefore, the absolute value of gamma prime of t dt this thing is less than or equal to this thing is less than or equal to these things. So this thing is less than or equal to this thing. Okay. Now, this thing over here is the same thing as this thing, because y prime, when you take its integral, is going to give you gamma of xi minus gamma of xi minus 1 by the fundamental theorem of calculus. So it's going to give you this thing. And we know that gamma prime of xi minus gamma prime of gamma prime of xi minus gamma prime of t is less than epsilon by this statement over here. So if I'm correct, there's actually so this is going to give you epsilon delta xi plus this other epsilon delta xi is going to give you 2 epsilon delta xi. So we're going to get this statement over here, and this is actually the same thing as saying the integral from a to b of the absolute value of gamma prime of t dt is less than or equal to a of p gamma plus 2 epsilon b minus a. When because we're adding the integrals of xi minus 1 to xi to get from a to b. So this delta xi, eventually it will become just b minus a. And this thing, it will be the sum of all of the gamma xi minus gamma xi minus 1, which is basically this thing over here as a definition. So that's why we change it. So now, since epsilon was arbitrary, we get that this is less than this, and we've basically proved the other side of the inequality. So like this, and we show that a of gamma is equal to the integral from a to b of the absolute value of gamma prime of t dt. So the strategy here was to use two inequalities. One was using the fact that the absolute value is less than the absolute value, the integral of the absolute value. And then the other part of the proof was to use the notion of continuity, and then divide the integral into two parts. And one part, we know it's going to give you the sum of what we need, which is a of p gamma, and the other part will give us something with epsilon, and we divide into both sides, two sides, so that we can get one side to have an epsilon and the other side to actually be the sum that we're looking for. And that's how we prove the other inequality. So that's the strategy. Alright, now I wanted to show an interesting exercise which has to do with Holder's inequality, which is really important. So we'll discuss it now. We want to prove that if un is great, when 1 over p plus 1 over q is equal to 1 for p and q positive real numbers, and if u greater than 0 and v greater than 0, we have uv is less than or equal to u to the p over p plus v to the q over q. And how we do this is we use the function f of x equals ln of x, and we apply it on both sides. And we know that g of x is equal to negative ln of x is actually convex. So we apply it on both sides, and we get that uv is less than or equal to 1 over p u to the p plus 1 over q v to the q. Now, the second part is that if f is in R alpha and g is in R alpha, f is greater than 0 and g greater than 0, then the integral from a to b of f to the p d alpha is equal to 1, and the integral a to b of f to the p d alpha is equal to 1 is equal to the integral of a to b g to the q d alpha. Then the integral of a to b of f g d alpha is less than or equal to 1. And how we do this is we actually use this property that we just proved over here. We're going to have that the integral from a to b of f of g d alpha is less than or equal to the integral from a to b of 1 over p u to the p plus 1 over q u to the q. Here just replace u and v with f and g, and you're going to get we know that f to the p and g to the q are both equal to 1. So we're just going to be left with this times 1 over p plus this times 1 over q, and both of these things are 1. So it's just going to be 1 over p plus 1 over q, which will give you 1. So this thing is less than or equal to 1. And now we prove Holder's inequality. And when p is equal to q is equal to 2, this is called the Schwarz inequality as we've seen it. So the statement is as the following. The absolute value from a to b of fg d alpha, its absolute value is less than or equal to the integral from a to b f absolute value p to the p d alpha times to the power of 1 over p times the integral from a to b g absolute value q d alpha to the power of 1 over q. Get this thing over here. And how we prove it is we use the fact that the absolute value of the integral is less than or equal to the integral of the absolute value. And we can just divide the absolute value to be the absolute value of f times the absolute value of g, which equals to this thing over here. Because notice these things are constants, so you can just take them to be in the denominator without having any problem. So you're just going to be left with this. F to the p to the 1 over p is the same thing as the absolute value of f, same thing here. So these two statements are equivalent. Now, we use this inequality again. So this thing, the integral of u times v, like this, is less than or equal to the integral of 1 over p times this without having the exponent 1 over p and without having the exponent 1 over q, because we exponentiated them and did them times 1 over p plus 1 over q to get this inequality over here. And this inequality over here, this expression over here now, we can just expand it out and get that is equal to 1 over p times the integral of from a to b of f to the p d alpha plus 1 over q times the integral a to b g to the q d alpha divided by the same things now. See? It's really interesting. So you want to use this inequality to show that you can cancel out the denominators. That's the strategy. The strategy was to compare these by dividing them with inequalities and using this inequality over here to cancel them out. And this is going to give you 1. So this whole expression over here is less than or equal to 1. Multiply on both sides and boom, we have Holder's inequality, which is this statement over here, highlighted in blue. So that's pretty much it for this video. There are other interesting exercises which have to do with the Riemann zeta function, which is basically the sum from n equals 1 to infinity of 1 over n to the s. You can check it out. It's really interesting. And there's a really good hint on how to do the problem. So if you follow the hints, you should be able to solve it. And yeah, I hope you really enjoyed this video about integrals and that now you have a more advanced understanding of calculus. And see you in the next one. Bye.